As our next speaker, please welcome Anders Søgaard. Anders is computer science professor at the Copenhagen University and author of famous papers such as multi-level learning with low-level tasks and using millions of emojis to pre-train models. Household terms in any respectable boards very soon. Welcome, Anders.
Cool, thank you so much. Thank you so much, and thanks, Clement, for a great introduction. You basically said all I want to say, so I'll just add a couple of footnotes to the story. So far, I've worked on language models for many, many years. It's been kind of our own little secret. Now they're out in the open. This is a great time to sort of remind people why we started building language models in the first place. So language models is a form of generative artificial intelligence, more and more synonymous with generative artificial intelligence. But it's a thing that did not fall out of the sky in November 2022. It's been around for a very long time. So when people work on language models, there's kind of two reasons that they do that. A surprising number of us are interested in psychology or language or biology, interested in simulating biological systems to learn about biological systems. I'm not going to talk too much about that. But when we do this for reasons of application, there's one reason we do this. It is because we believe in the value of making as much information as possible accessible to as many people as possible in as many forms as possible. And it's important to remember that not too long ago, information was really hard to get by. It was a commodity. It was unevenly distributed. You basically needed an encyclopedia in your bookshelf or a library around the corner, and for most people on this planet, you had none of those. So of course, with search engines, information became available to an extent that we haven't seen before in history. But it's also important to acknowledge or realize that just because you have a search engine does not necessarily make information accessible to everyone, right? First of all, obviously you need a laptop, you need electricity, but you also need content that's available online in a language you understand. And you need to be able to read. And so many of us don't. There's, in Denmark, 400,000 people who say that they find it really hard to read. So it was sort of a natural next step to think about speech-based interfaces, but even so, information is not necessarily accessible to everyone. I'm sure that most of you, on a day-to-day basis, write documents that I would find it really hard to understand. I occasionally write stuff that's really hard for my kids to understand. That's why we have teachers. That's why we have tutors. But the problem is that's a scarce resource. It's a bottleneck. We don't have enough of them. On a day-to-day basis, I give lectures for 500 students. I wish I had one-on-one conversations with them. I don't. And that's why we wanted to build dialogue systems, because they're basically for making sure that you understand the stuff that you're interested in out there. And I think with this sort of package or this toolbox, we're finally at a point in history where information is really becoming accessible in a very general sense. And I think AI really has that potential to become a great equalizer. I got a dyslexic PhD student. That was an uphill battle just 5 years ago in academia. And I think that's really fascinating. So that's why we're doing all of this. As I said, this is not a new technology. It's not a new idea. Language models or neural networks, they've been around for a long time. This is Frank Rosenblatt in the 50s in upstate New York implementing some of the first. This is probably redundant for some of you. Neural networks are function estimating algorithms. And they're sort of a general purpose tool. For those of you who don't know what that means, we've all done function estimation. I did it in 5th grade in math classes in elementary school. We would be presented with small little challenges, such as here's a row of input numbers, say 1, 2, 3. Here's a row of output numbers, 11, 12, 13. Which function is going to take you from the input to the output? Those kind of problems. And the smart student would say, that's f on x equals x plus 10 or something, and that's function estimation. That's what neural networks are for. Language models or chatbots are function estimation algorithms. They estimate functions from context to text. The nice thing about having a function is that once you have it, you can throw more stuff at it. So once we have our function, the +10 function, we can throw 4 at it, out comes 14. We can throw 5 at it, out comes 15, and so on. Now, that's not really a chatbot, but let's just pretend that these numbers correspond to words. OK, so 4 corresponds to the word cat, 14 to the word cute, 5 to dog, and so on. OK, now all of a sudden we have a function that if I say cat, it's going to respond cute. OK, these are kind of one-word utterances, but it's kind of like the same conversations I have with my teenage son on a day-to-day basis. The trick, if you want this kind of function to generate longer text, is just to apply it multiple times. Because if we stick in 4, out comes 14. We can turn that into input, and out comes 24. We can stick that in, out comes 34, and so on. And that's basically what a chatbot is. You probably know that these are deep neural networks. That just means that inside this guy, there was a guy like that in my kind of math textbooks when I was in elementary school. Inside this guy, there's more than one function now, right? So if this is the input numbers and the output numbers, it's not just one function taking us from the input to the output, it's multiple functions. And all of a sudden, there's multiple solutions, right? So you can have f on x equals x plus 3, and you can have another function called g on x equals f on x plus 7, for example, or it could be plus 2 and plus 8, and so on. OK, that's basically a deep neural network, except for nonlinear activation functions that I'm not going to talk about here. Cool. OK, so neural networks have been around for a while. So have language models. This is my, or something very similar to the kind of cell phone I had when I was in high school. They had language models too. They had a language model patented by Ericsson in '88, I think, called T9. And that was because they had 12 keys. So if you wanted to write something like good, you would have to push like 4 and then 666, and then pause for a moment, and then 666, and so on. That was super annoying. So it was kind of cool if you could just do 4663 for good. But the problem with that sequence is that that potentially corresponds to many words, right? So a word like home would correspond to the same sequence. Now, how do you guess what people intend to write? You use a language model. The language model back then was very, very simple. It was basically a giant lookup table with sequences of keystrokes and the words that would correspond to that keystroke sequence ranked by their probability. So this was just the number of occurrences in some random text corpus. Back then, digital text was Newswire, so you just took a lot of Newswire, you counted up occurrences, and that gave you your ranked list. I don't know, if there are Danes in the room, you probably remember receiving messages that would just say "øl." Do you? Kind of, if you're old enough. That's because that corresponds to the same sequence as OK, and apparently there were more beers, so øl is the word for beer in Danish. There were more beers in the Newswire data than there were OKs. Now, the reason the language models were so simple is because memory was super limited on these phones. As phones grew or kind of gained more capabilities, we could increase the context that we can condition on. Because the word good and the word home, they have different base probabilities, but in certain contexts, that's going to change. So in the context of the word go, for example, home becomes very probable. So we started conditioning on more and more context, basically solving this other problem from elementary school called fill in the gap, right? So you have a sentence, there's a word missing, you want to predict what's missing. So in the context of he, for example, you'll have walks and talks and so on be very probable continuations. Basically what's happened over the last 5-6 years is that with better and better hardware, we've been able to condition on more and more. So now when you write a text message, we're conditioning on the entire thread. But also, we're now going beyond the linguistic context. So we're conditioning on stuff that's not even in the text. Because it turns out that the situation we're in, or who we are as people, really is very important for figuring out what the most likely intention behind a text is. So when I'm here in front of you today, I'll use the word language model or the word GPU with much, much higher probability than tonight when I talk to my 7-year-old. The fact that I'm a professor of computer science also means I talk a lot about language models more than people do on average. So knowing that is really important. So we started conditioning on these things. We call it conditional language models. And that sort of become available because of transformers and GPUs, scaling up. So now we're not just conditioning on, say, the word he, but he in a particular context. This could be in the context of legal text processing, where all of a sudden the probabilities change, and you will have words like appeals and adjudicates and so on become very frequent. Or in the context of 9th century literature, you'll have words like saith and haith and so on. We might also want to know about the application you intend to use the language model for, and if this is machine translation, for example, maybe the continuation is not even an English word, but say the word er, which would be the German translation of the word he. Okay. As hardware has become better and better, we are starting to see something really fascinating, or we've seen that for about 5 years now, where we started, so Jonathan mentioned a paper of mine on multitask learning. We started to see this idea that we can get neural networks to do multiple tasks at the same time. Now, in order to do that, we need all the different tasks that we're interested in artificial intelligence, be it machine translation or sentiment analysis or search engines or speech synthesis. We need them to kind of live in the same input format. Now, the natural intuition that's been guiding the research the last 5 years is that a really good format for basically all problems on this planet is basically Q&A, right? So you can turn any kind of problem into a question and the answer to that problem into an answer. So the idea of building Q&A systems as sort of a universal format for all the stuff that we're interested in AI has really driven the development over the last couple of years. So instead of seeing Google Translate or like machine translation as something like with a drop-down menu and where you're configuring the system to do German to English translation, you just have a general interface and you ask for the German translation of a particular sentence in English. Okay. We can now condition on so much context that we can also provide instructions to the models as part of the context. So this is what happens in GPT-4 or something where when you condition on, say, annotation guidelines or guidelines for solving a task in a particular fashion. So the machinery is still the same. We're still doing the same language modeling problem as you did back in the T9 language model of the Ericsson phone, but we're conditioning on a lot of context, including information about the situation, who's using the software, what they're using it for, possibly with instructions that are very detailed. That's language modeling. It turns out you can do the exact same thing for other modalities. Now, why is language modeling such an interesting task? Well, because to do that fill-in-the-gap exercise, you need to know a lot. You need to know a lot about morphology, syntax, semantics, pragmatics, in order to figure out what's missing in a text, right? I say, a frog jumped out the, and you need to guess what's missing. You need to know a lot about English, morphology, syntax, semantics, pragmatics to figure out what's a possible continuation for that sentence, because there are things you jump out of, and there are things you just don't jump out of. The same holds for figuring out what's missing in that image. When I delete a random part, you need to know a lot about cats to fill in that pixel patch. You need to know a lot about sounds to kind of fill in missing parts of a sound bite. Increasingly, we're starting to see all of this come together. So our neural networks can now represent different modalities and output different modalities. And increasingly, we're starting to see that they converge in how they present us. So one of the big business potentials of language models is that they become a universal translator between different formats, making software development a lot easier because they become a medium here. I can talk more about that. Okay, so just to wrap up this sort of introduction to the history of artificial intelligence, I think in a beautiful way, AI is sort of coming full circle. When AI started in the 50s, there was this grand vision of building kind of software that could do all the stuff that we as humans can do, all the stuff that sets us apart from all the other species on planet Earth. Things like proving mathematical results, composing music, translating between different languages, and so on. It turned out that doing so in Prolog code was an uphill battle, so the field kind of compartmentalized. Then we had research groups doing chess computers, and research groups doing theorem provers, and research groups doing machine translation. But today, we're actually starting to build models that do all of this in one go, and we're exploiting the synergies between all these different tasks. I personally find it ironic that this is in the form of chatbots. If you remember what a chatbot was like 10 years ago, like that little thing in the lower right corner on IKEA's website. But the reason for it is because they do question answering, and you can turn any problem into a question answering problem. When you want to assess the opportunities and challenges that a technology such as language models is facing us with, one question that keeps coming up is whether these models have any idea about the environment that we as human beings are part of. Do they understand the world we live in? And I told you about functions. I told you this is mathematically just addition and multiplication. It's really the same thing that we did in 5th grade. In some sense, these are really, really simple. So we estimated the function with 2 variables, a coefficient and a cutoff. These have millions of variables, but the mathematics is the same. And in some sense, they are just the same technology that we had on our Ericsson phones. They're just writing support tools in some sense. On the other hand, if you've talked to Palm 2 or Llama 2 or ChatGPT, it's kind of like almost talking to a real human being. And human beings are great because they have some level of understanding for the world that we're part of or that we share. So do language models understand the world that we're in? There's a lot of stuff confronting us with language on a day-to-day basis that we don't deem intelligent. There's, a piece of paper can confront us with language. We don't think the paper is intelligent. A parrot is super intelligent, but not in this sense. But it also confronts us with language. Of course, part of the game here is you need to be coherent. You need to be able to use language across a lot of different domains in adequate ways. But you can even imagine doing that and still sort of faking linguistic competence. Philosopher John Searle came up with this thought experiment where he imagined that he would be in a room with a Chinese parlor, receiving Chinese characters as input, providing characters as output by basically looking up in his parlor what sort of an appropriate response to a particular Chinese character without having any idea about Chinese, right? Whether this is a good thought experiment or not, or whether it's useful, I don't want to go into that discussion. I just want to remind you that we can sort of imagine what it would be like to be a dialogue partner and fill that role without having any understanding. Basically, what faking language would be like. So there's a lot of people discussing this question right now, but I want to talk a little bit about why it's complicated. This is sort of like where it gets the peak of complexity in this talk. We've done a lot of experiments in our group trying to address these questions, and one of the things that we've done is we've compared the conceptual encodings in language models with the conceptual encodings of computer vision models. So the idea is, very briefly, that you can throw words that correspond to concepts at language models, and you can look at the activations inside these functions. So these activations, kind of like that function we just had, the f on x equals x plus 2, you can represent them in 2D as a line. And in the same sense, you can represent all these activations corresponding to different concepts in language models as points in space. So you can think of them for now as points in 3D space. In reality, it's going to be like 1,000 dimensions or 5,000 or 100,000 dimensions. But just imagine sort of a cloud. Let's put it over in this part of the room, which is basically just a lot of concepts and how they're represented inside our language models. Okay, so we got a bike up there, we got a space rocket over there, and so on. Okay, now we can do the same thing with that computer vision model I just told you about. Okay, so the language model is just trained on sentences where we remove some words, we predict. We get a neural network, we represent. So over here we have a computer vision model. We do the same thing. We take a bunch of images, matrices of pixels, we remove patches, we train a neural network, and we have activations for different concepts. Okay, so we take a concept like bike, we take 5 images or something, and we look at the average activation, and we put bike up there. Okay, so now we got 2 clouds, and they will have some geometries. Okay, maybe one over here is S-shaped, maybe the other one has a slightly different shape. Now what we do is we can do Tetris, kind of like the computer game, and we can rotate and scale one of them to see whether we can get them to align. Now it turns out that the better the language models are, the more you can align these things, and if you do so, things will match up incredibly close, to the extent that for 2 and 3 words at least, the corresponding concepts will align next to each other. What does that tell you? It means that these models are learning a lot of the same stuff, in spite of the fact that one only saw language, the other one only saw images. Now, how can that be? Well, I think the story is both the language and the images are embedded in the world, and what these models learn about is the world. So it turns out that you can also take a language model, and you can look at things like how do the words corresponding to, say, the capitals of Europe embed? If you do that, you print out the vectors, and you do dimensionality reduction down to 2 dimensions, you get a pretty nice map of Europe. Okay? So these models actually learn stuff about the world. There's vectors corresponding to space and time and so on. These are just graphs showing you that the bigger the language models get, the more the similarity will increase. We've done similar experiments where we put people in brain scanners and we look at the neural response measurements from something like fMRI. You can also vectorize that. You can create the same kind of cloud, and you can do the same kind of experiment. And again, we have this effect that the bigger the language models get, the more similar they are to the neural response measurements. What that means is that this concept organization is also very human-like, at least as far as we can estimate what's going on inside the brains of human beings. This is useful for things like brain decoding. We can basically read every second word that people think about when they read Harry Potter or listen to podcasts. Okay. Because of the structural similarities between how things are encoded in language models and how things seem to be encoded in our brains. Okay, so somehow these models are just more than grammar checkers. We know that they're good. We know that already, right? So you can throw different exams at them or different tests, and they outsmart humans. They're better than not just our average students, but some of our best students. And there's a lot of stuff that they're particularly good at, and we're starting to see the impact on that. We're seeing the impacts in software development, in graphical design, and customer support, and so on, all tasks where we can sort of roll these out pretty easily, and they can do stuff for us. They can help us. We're also seeing that there's a lot of bars that are being lowered by language models. So it's easier to become a software developer today. It's easier to become a PhD student. It's easier to become a writer. It's easier to work in a language that you didn't speak for 30 years. So of course, there's a lot of sort of movements already, a lot of short-term effects. There's also challenges in the software industry for companies doing different types of software development, and there's a lot of kind of new jobs around these technologies. I don't want to talk about that because that's boring. I kind of echoing Clement, I think we should talk about the long-term potentials instead, because obviously there's a lot of investments in AI right now, and things will go fast. Hardware increasingly gets better, algorithms increasingly get better, things get faster and faster. And we're no near the physical limits to what's possible, right? So a laptop can do 10 to the power of 9 computations per second. The human brain, 10 to the power of 11. If we put all our brains together, we have 10 to the power of 20. I think the physical limitation to what you can do in a kilogram of hardware is 10 to the power of 50, right? So if this sort of continues, in not too long, we'll be able to do much more than humanity, but also much more than humanity in 1,000 years or 10,000 years or 100,000 years. It's difficult to predict the future, but I think we already see some interesting contours that I think we need to think about. There are new industries emerging in Silicon Valley. There's a lot of talk about digital relations, digitized selves, personalized worlds. This whole idea of brain decoding is certainly something that a lot of companies are investing in. There are real concerns around a lot of things. I'll just talk about 3 of them here: inequality, manipulation, and cybercrime. Digital relations is big business. There are a lot of companies offering chatbots equipped with personality, equipped with an avatar, a 3D environment, mono-threaded history, so that when you open up your chatbot, unlike ChatGPT, if you said yesterday you're going to a party, the first thing it's going to ask you is, how was the party yesterday? So you have a much more natural conversation. These are all sort of sold as your new best friend, your new best lover, or someone who's going to train your social skills. And they have millions and millions of users, and if you talk to them, they're all super happy. They've never felt this met before. And they're also starting to lose interest in their social physical relations often. So that's definitely something to think about. There's the notion of the digitized self. We are already using ChatGPT to respond to our emails. Some of us do it in a fully automated fashion. So that's a token of trust. And we do so because we expect ChatGPT to sort of be aligned with our preferences. The more that we can align these language models with our preferences, there's this whole question of what are we willing to have them do in a fully automated fashion on behalf of us. Can we imagine sort of having language models do shopping for us, or do investments, or interior design, and so on? There's a lot of companies betting on this. They call it digitized self. So the idea that we can condition in this context, that we're conditioning on personality profiles that are accurate enough that we're aligned with user preferences. If you have one language model, of course, you can have many, and you can have a whole world of language models interacting. Of course, that's potentially entertaining, and the gaming industry, of course, is very excited about the opportunities here, but also social scientists use this for modeling social dynamics, for example. There are a lot of questions around inequality when it comes to AI. The technology itself is unevenly distributed. That's why there is an export war between the US and China right now around GPUs. But also, if you look at the top research groups, they're unevenly distributed. So there's going to be inequality at the global level, but there's also inequality at the national level between different social groups. So Danish speech technology, for example, finally works. That's great news. If you're young and you live in Copenhagen or Aarhus or one of the other big cities, because then it works. Preferably, you should be male too, then it works really well. But if you're 50 plus and you live in Northern Jutland and you just learned how to speak Danish 10 years ago, it's terrible. Now, that's a democratic problem because we are in the process of becoming more and more reliant on technology that's going to work much better for some of us than for others. So that's really important. And of course, one of the things that people talk when they talk about how to best regulate AI. Manipulation is something that I'm super worried about. So these language models are generally trained to just predict the next word, but they're also being rolled out in the context of a lot of companies that have slightly different business models right now that are generally optimizing their technology, their models to keep people engaged. So when Netflix uses a language model or when Snapchat uses a language model, the very obvious thing for them to do is to have a reward signal to keep the models engaged with their audience as much as possible. Now, when you do that, any kind of strategy works. We are biological creatures. There's a lot of buttons that we can push. There are a lot of buttons that are constantly being pushed when we go out in the world. So you go to the bakery store, there's a donut. It's pushing a lot of buttons that are there for natural reasons, right? So fat is important for us, sugar is important for us, and from an evolutionary perspective, it makes a lot of sense to have those buttons because there are no donuts out there in the real world. It's called a supernormal stimuli in the context of biology. My favorite example is birds. So birds lay eggs in nests. It turns out that they pay more attention to the big eggs because they have a higher chance of surviving. Now, in the 50s, there was a zoologist who designed a synthetic egg and put it in the nest of some birds. What would happen is that this bird would just jump on that synthetic egg because it was so excited. It pushed all the right buttons. Now, it was too big to sit on, so it would kind of slide off, right? It would be equally excited and jump back on. It would slide off, jump up, slide off, and so on. Meanwhile, all the natural eggs would die. And I think we need to worry a little bit about the potential of these general-purpose technologies when they're optimized for engagement, because if they pick up on strategies that will, in fact, keep us engaged, finding out what strategies they picked up on is going to be really hard because it's going to be hidden in millions and billions of variables. These models are, in that sense, not so transparent. The final risk that I wanted to mention here is cybercrime. It takes about $30 a month to be a good cyber criminal. If you think about love scams, I think last year Americans lost $500 million in love scams. As a love scammer, you can probably have 30 conversations at the same time. Now with these tools, you can have maybe 10,000. You can not just do text-based love scams. You can add in voice cloning. You can add in image editing, and that gives you a very convincing story. What I'm really worried about, though, is when cyber criminals figure out that they can optimize all these things to do as well as possible. So they can run 10,000 love scams, figure out what works and what doesn't, and reward their models for strategies that work. And they learn strategies again, appealing to subliminal influence, and we can't figure out what the strategies are, it's going to be really, really hard to push back. So these are just some examples of things that I think we need to worry a little bit about. That's it for what I had to say first time around. Thanks.